And welcome to today's lesson. In this first tutorial, we will be able to graph exponential functions. This is going to be for when a equals to 1, and we will be able to state the domain and the range. So we are in section 7.1 and 7.2 in our textbooks, graphing exponential functions. Oh, it looks like somebody did not complete my title. It says fun here, which of course we will have, but I actually meant functions, so that's a little bit better. Okay, so when we're talking about exponential functions, we're talking about the basic function, which is f of x is equal to b to the x power. So our base is b in this case, and of course because it's exponential we have our variable in our exponent. I'd like to look at the graphs of these in this tutorial, and I'd like to do that through 4 examples: f of x, and g of x, h of x, and k of x. I'm going to graph the first 2 on this first graph patch and the second 2 on the second one. And I am going to color code, and I would suggest that you do the same. I'm going to make f of x in red here. Our base for f of x is a base of 2. So we're talking about the powers of 2. And if you need your power chart to help you with this, that's absolutely fine. So we're talking about the base of 2. I get to plug in whatever I want for x. So I'm going to start with 0 and move into some positives and then do some negatives. So let's start with 0. 2 to the 0 power, in fact, anything to the 0 power would be 1. So when x is 0, my first point that I have is 0, 1. So that's my first point. Let's move to the first exponent, which would be at when x equals 1. 2 to the first power, of course, is simply 2. So when I go to the right 1 unit, that represents the first power, I'm going to go up 2 units because 2 to the first power would be 2. Next, I'm going to go to the second power, which is going to be 2 squared. So second power means that I'm going to the right 2 units. 2 squared, of course, is 4. 1, 2, 3, 4. And there's my next dot. Let's go to the third power, which is cubed. 2 cubed, we all know, is 8. So I'm going to go 3 units to the right and go up 1, 2, 3, 4, 5, 6, 7, 8. And let's see if I can do maybe one more. 2 to the fourth power, 2 times 2 times 2 times 2 is 16. Let's see if I can do that. 1, 2, 3, fourth power. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Look at that. It just makes it. If I went to the fifth power and the sixth power and the seventh power, they'd be off my graph patch, but those outputs do exist as well. Now let's talk about what if we put in some negative exponents. For example, 2 to the negative 1 power. When you see a negative exponent, you should remember that it's a reciprocal value. So 2 to the negative 1 exponent is actually 1 over 2 to the positive 1 exponent, or rather 1/2. So when I go over negative 1 to the left, I'm going to go up a little half. And 2 to the negative 2 power, similar, I've got the negative exponent, which means it's going to be a fraction, but this time it's 2 squared in the denominator, and 2 squared, of course, is 4. So 1 over 4 would be my output, and then 1 over 8, and then 1 over 16, and then 1 over 32. Basically, the reciprocals of each of the outputs that I had here are going to be over here, getting tinier and tinier and tinier. Hopefully you believe me that there's no way that this is going to cross or even touch the x-axis, so therefore we have a horizontal asymptote here for this graph. I'm going to do it in a different color. And we're going to find that that horizontal asymptote is true for actually all 4 of these graphs. But we'll get tinier and tinier and tinier, but we will never actually equal to 0. So this is our first exponential function. We start very close to the x-axis, and then we start to increase exponentially and increase very, very fast. Let's graph the g of x graph, and I'm going to do this one in blue. Perhaps you're choosing a different color. The only difference now is our base is 4, so we have a different base, but it's going to be the same idea. We're going to plug in a 0 and some positives and some negatives. So let's do 4 to the 0 power first, which of course we all know is 1. Anything to the 0 power is going to be a 1. Now when we go to the first power, our base 4 to the first power would just be 4. So going over 1, we go up 1, 2, 3, 4, so a little bit higher. Let's go to the second power, and you can already see that the second power is going to make us go to 16, because 4 squared is 16, and we know 16 is all the way up here. So this is getting higher even faster than when the base is 2. So the connection is as the base increases, our graph will exponentially go even faster up. Let's go to the negative side. Let's do 4 to the negative 1. That is going to be equal to 1 over 4. So that's technically a little bit lower than my existing red dot. And then 4 to the negative 2 would be 1 over 4 squared, which is 1 over 16. And that's even tinier than the red dot. Even though it's still underneath the red function, it's still never going to touch the x-axis. I'm going to graph a little bit underneath the red, and then it crosses at the 1, and then starts to be above the red and getting up even faster. So there we go. Same horizontal asymptote. Let's talk domain and range. We can plug anything we want for x. There are no restrictions for x. So therefore our domain is the set of all reals. We can do that with the big fancy capital R, or we can do that with our interval notation from negative infinity to positive infinity. The range, on the other hand, is restricted because we do not have any negative outputs. In fact, we don't even have the value of 0 as an output. Our range starts at 0 and then goes up infinitely to positive infinity. So we could do the set of all y such that y is greater than 0. It's basically saying that everything positive works, but not the 0. Or if you'd rather do interval notation, we would start with the parenthesis and go from 0 to infinity. The parenthesis meaning that 0, again, is not included. So this is what our basic exponential equation looks like when it's graphed. It has the horizontal asymptote, which is basically the lower boundary. We're not going to get lower than that. And then the curve bends up like this and starts off, it's always increasing, but it's increasing very slowly at first until it crosses over the middle value, I guess that value of 1, and then it increases very much. Let's see what happens over here. I'm going to color code again. H of x I'll do with red. This time our base is going to be a fraction, and I'd like to see what the graphs look like now. So our fraction, our base, is 1/2, and we're raising that to the exponent of x. So let's plug in a 0 and some positives and some negatives the same way. So 1/2 to the 0 power, again, that's going to be a 1. 1/2 to the first power, so when I go over to the right 1/2 to the first power is just itself, so that's 1/2. And then when I do 1/2 squared, 1/2 squared is 1/4, and then the next one would be 1/8, and then 1/16, and so on and so forth. So it looks like we're decreasing down this way, and again, we're never going to be touching 0. We get tinier and tinier fractions, but never equal to 0. But what happens when we take 1/2 and go in the negative direction to the -1 power? Well, again, a negative exponent means reciprocal, so we take the reciprocal of the base, which is just 2 to the first power. So when I go left 1, the -1 power, I get to go up 2. And when I go left 2 units, that's 1/2 to the -2 power, that would be 2 squared, which would be 4. So when I go over 2 to the left, 1, 2, 3, 4 is my output. And then my next output would be 8, 1, 2, 3, 4 more. And then my next output would be 16, 1, 2, 3, 4, 5, 6, 7, 8 more. So you can use your power chart this way. It just happens to be backwards. Same sort of thing in terms of the horizontal asymptote. We're never going to be touching the x-axis. I'm going to put the asymptote a little bit lower than the x-axis so you can see it. And then our curve is decreasing very much at first. And then once we cross the y-intercept of 0, 1, then we start to decrease a little bit slower. Still decreasing forever. That's why I'm going to put the arrowhead, and I'm going to put the arrowhead over there. So it looks like when we flip our base, our graph flips direction as well, and we're decreasing now. Let's look at k of x, which is the reciprocal base of our g of x4. Now it's 1/4. Same thing, let's plug in a 0, which of course we're going to get the 1. When I plug in the 1, 1/4 to the first power is 1/4, so we're a little bit lower than here, and then 1/16, and then 1/64, and so on down my power chart. But when I flip over and do 1/4 to the -1, that's again going to be the reciprocal of my base, which is just 4. So -1 1, 2, 3, 4, and negative 2, which would be the reciprocal of 4, but squared. So we get those same values just on the opposite sides of the y-axis. We are decreasing very much till we get to the y-intercept. Then we're going underneath the red curve and continuing to decrease for the rest of the way. I know it gets kind of tight right in there, but there you go. If you're looking at the domain and the range, they actually have the same domain and range. The set of all reals for the domain, because we get to plug in anything we want. And it doesn't matter to me if you want to use the set notation or the interval notation, and the same exact range, all y, such that y is greater than 0, or you could do your interval notation, which I tend to do this time because I feel like it's a little bit less writing there. I'd like to look at two examples. But before we do that, we should look at the general form. The general form, so that we have all three of our parts like we normally do with our graphing parts, we have an a, and that's going to be the coefficient that's multiplied to my base. And the base is always going to be to the x minus h power. And then we'll have our k added out here. This is our general form, and just like all of our other forms that we've looked at when we're graphing by translations or transformations, A does something, H does something, and K does something. A affects the outputs, like normal. So whatever our normal outputs would be, we multiply by A, and that's how A affects our graph. H is our lateral shift or our horizontal shift, since it begins with H. I'll say H shifts left and right. Watch out when you're trying to find the value of H, because remember it's in here with the X, and you have to take the opposite of what you see here. If you see a minus sign, H is positive. If you see a plus sign, H is negative. K is just the number that's sitting out here. There's no opposite idea here. It's just positive K. Whatever K is, that's what it is. And that, of course, shifts us up and down. So that's what A, H, and K do, just like all the other graphs that we've looked at. So let's look at A of X. What I've done here in example 1, I'm going to use the same parent function. This time the base is going to be a 3. If I use the same base 3 for all of these, you can see base 3 here and base 3 here, and in the other two that we're going to do, then we're using the same base for each one of them, and we can see just what A, H, and K do. But we'll be graphing with different bases throughout. We've already done a base 2 and a base 4, a base 1/2, a base 1/4. Now we're going to look at base 3. So let's find A, H, and K first. We should always be able to find A, H, and K to help us. So the value of A is always the number that's being multiplied to my power here. And since you don't see anything, it must be A is equal to 1. And that's what we're looking at in this tutorial. So that means that our regular outputs are going to be multiplied by 1 and remain our regular outputs. H is always the value that makes this exponent equal to 0. So that's why H is a negative 1. Some people just realize that it's the opposite of this symbol here. So negative 1, there you go. K, I don't see a K out here, so it's like plus 0. So K must be 0. So what I like to do with my H and my K is realize that since H takes me horizontally and K takes me vertically, that the value of H and K become like my new origin. And what I like to do with that is I like to plot that point. I don't actually plot a point. I draw a box, because it's actually not going to be a point on my graph, but it's going to be like my new starting point. It looks like my origin has just shifted over to the left 1 unit. As soon as I know where my starting point is, or my box, actually sometimes I just draw a star. I think that's what we've done before, so maybe I should do that. Let's draw a star for our starting point. That makes sense. So when I have that, I know that that's where my horizontal asymptote will go. It'll go right through the star. So I'm going to plot that in first, and then everything else just depends on what the base is. Since my base is 3, I'm looking at the 3 on my power chart, and my special values for the powers of 3 are 1, 3, 9, and 27. Very rarely would I use the 27, so it's really just 1, 3, and 9. So what I do for my star is I go 1 unit above the star is my first point, And then from the star, I go 1 unit to the right, and that's like my first power, which would be 1, 2, 3, because 3 to the first power is 3. And then I go back to the star. I always start at the starting point, and then go 2 units. That's like 3 squared, so I get to go up 1, 2, 3, 4, 5, 6, 7, 8, 9. I'm not going to be able to fit the 27. Over here, technically what the points are 1/3, 1/9, and 1/27th, but I'm never going to be able to whip out a ruler and actually measure that you've got that correctly, so I kind of call these the cheat points. As long as they're there, I can't really take off because I can't, measure exactly 1/27th of a tick mark. So just put them there, know that they're getting smaller and smaller and smaller to the x-axis, or to the horizontal asymptote, I should say. As long as they're there, I cannot take off for that, and there you go. So it looks identical to one of the other ones except different values, but this one has shifted to the left 1 unit. Let's look at b of x. B of x is 3 to the x minus 2. Now some books or some worksheets will have the -2 come first, so that you don't confuse that this is not a value of h, but rather that it's a value of k. So you might see that in 2 different ways like that. Let's look for a, h, and k. A is still the number that's being multiplied to my base, and that still is just a value of 1, since I don't see any value outside that. So A is 1, which is nice. H, this time there is no H up here that I see, so it must be 0. And K is the number -2. So this time my starting point is 0, -2. So I go down here and I draw a little star. So my origin has actually shifted down 2 units this time. Once I know where my star is, I put my horizontal asymptote right through it, and nothing is going to touch that horizontal asymptote, not for an exponential function. And then we just need to know what the base is. Again, the base is a value of 3, so we're looking at the same powers, 1, 3, and 9. Starting from the star, I go 1 unit above, and then 1 unit to the right, and we get to go up 3. 1, 2, 3. Back to the star. 2 units to the right, and I get to go up 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. I'm not going to fit the 27 again. Very rarely would I be able to do that. And over here, I'm just going to put my cheat points. Technically, they're 1/3, 1/9, and 1/27th. But as long as you put them there, getting smaller and smaller, can't do much about that. And there we go. Thanks for watching this first tutorial when a is equal to 1, and we'll look at 2 more in the next tutorial. See ya.